Okay, so today we're going to be looking at periodic trends and just taking a look at a couple of those. We won't look at every single periodic trend that exists, but um, four of them and how they relate to each other and kind of how you can make sense of the periodic table based on trends. So, before we get into this, some terms that you should know by now. You should know valence electrons. These are the electrons found in the outermost energy level, highest numbered energy level, right? They're also furthest from the nucleus, and they are the electrons that are actually participating in chemical reactions and bonding. The next one, effective nuclear charge, or Z effective, and that is how much pull from the nucleus the valence electrons are actually feeling or receiving. And what would change the amount of charge from the nucleus that valence electrons are feeling is what's called shielding. And so shielding, that's when the core electrons, right, that's anything that's not a valence electron, is essentially blocking the nuclear charge from reaching those valence electrons, right? So the valence electrons are being shielded by the core electrons. And then the last one, electron repulsion. So just as with magnets, right, electrons, as they are all negative, they repel each other, right? I think you probably have all tried pushing two magnets together on the same pole, and it's kind of tough to do. And that's what's going on with electron repulsion, right? They are actually pushing each other away because they have the same charge. So the first of the periodic trends that we are going to look at is atomic radius, right? And that is the radius of an atom, the distance between the nucleus and the valence electrons. And so the general trend of this is that atomic radius decreases across a row, right? So like going from, on your periodic table, like lithium over to fluorine, right? They get smaller as they go across, right? So the atomic radius decreases across. However, increasing down, right? So like going from lithium down to francium or francium, as I've heard it called, those are going to get larger in radius, right? Just like this diagram here. And so that's the basic trend. And so why this happens? So why does this happen is because as you're going across, right? You know, if you've got your nucleus and you've got your rings, right? You're adding electrons for every element you go over, but you're also adding charge to the nucleus, right? And because these rings are not getting any further away, essentially you're just adding strength to the nucleus to pull the electrons in closer. And so that's why they're getting smaller as you go across. And so larger going down, right, we can think of this the same way. Because every time you go down one element in a row, you're adding an energy level, right, or a ring, right? So like 1, 2, 3, 4. And so every time you go down one element in a column, you're essentially adding an energy level, and those valence electrons are getting further and further from the nucleus. And so the nucleus has less of a pull on those valence electrons, and the radius increases. And so that is why that trend is the way it is. So the next one, ionic radius, this is really similar. It's the distance between the nucleus and the valence electrons, except this time of an ion. So for this one, the general trend is split into metals and nonmetals. And for each group, right, the radius decreases across a row and increases down a column, just like atomic radius, and for the same reasons. However, with this one, there is one extra thing. So metals, right? Cations, positive ions, they are always larger, or sorry, I'm going to stop talking for a second. Let me start again. Cations, right? Metals, they form positive ions. They are always smaller than their neutral counterpart. And why this is because metals, remember, they're losing electrons to become positive. So basically, you're losing negative charge, but you still have the same positive charge. And that means that the nucleus can pull with more force. And so it actually pulls in the remaining electrons closer. So the opposite is true with nonmetals, right? These form anions, negative ions, so they are always larger than their neutral counterpart. And that is because to become a negative ion, right, you're adding electrons, but you've still got the same amount of charge in the center here. And so those electrons, right, the center is not pulling with as much force, and those electrons can push away from each other more. And so your radius increases compared to neutral when you have a negative ion. Okay, this one, ionization energy. It is the energy required to remove the outermost or highest energy electron from an atom. So the general trend is that it increases across a row and it decreases down a column. So basically, it is really tough to remove the outside electron from that stuff over here, right? But it's really easy to move electrons from the stuff over here. And so this kind of fits in with other trends. Like if we think about radius, right? You've got your smallest atoms over here, which means the electrons are going to be closest to the nucleus, and so therefore held on with the most force, and so you will have a tougher time pulling those electrons off of an atom. Whereas over here, we have some of the largest atoms, and because of that, right, their valence electrons are very far from the nucleus, and so not held with much force, and so they're going to be really easy to remove from those atoms, right? So smaller atoms, tougher to remove electrons from. Larger atoms, with the electrons further away, easier to remove. Electronegativity. So this is one that it's important to remember. We're going to talk about this one a lot again when we talk about bonding, because electronegativity has a lot to do with bonding. And you'll see that in the definition here, because it is a measurement of how strongly an atom can pull electrons to itself in a bond. As this only occurs in bonded atoms, noble gases are said to have no electronegativity. So, for this one, just like ionization energy, the general trend is that it increases across a row, right, left to right, and decreases down a column. So there's a reason why fluorine is listed here. Because the noble gases do not have electronegativity, fluorine is the most electronegative atom on the periodic table. So electronegativity, again, just like with ionization energy, and again connected to atomic radius, where smaller atoms, right, like fluorine, where their valence electrons are close to the nucleus and held with a lot of force, right, they have a high effective nuclear charge, they're going to have a lot of electronegativity. They're going to pull electrons from other atoms towards themselves with a lot of force when they're in a bond. Whereas things down here in this corner, like francium, that their valence electrons are very far away and they are not pulled with much force. They have very low effective nuclear charge. Right, they are going to have extremely low electronegativity because they are not going to pull electrons towards themselves with any kind of strength at all. Okay. So from my descriptions of them, you may have gathered kind of how all of these are related. So, but looking back, all right, hopefully you notice as the atoms and ions get larger, they're easier to remove electrons from and pull electrons with less force. All right, all of this is due to effective nuclear charge, right? Like, remember the beginning I started with that, how strongly the valence electrons are actually feeling the pull from the nucleus. And so as valence electrons get further from the nucleus and there are more core electrons to shield those valence electrons, right, the pull from the nucleus gets stronger. So therefore, right, they're larger. It takes less energy to remove electrons from them. They pull with less force. It's all due to effective nuclear charge. Okay, you might be wondering, why am I even talking about this? Okay, periodic trends, as I say here, help us predict how reactive an element will be, right? Those with very high and very low electronegativity tend to be extremely reactive. It helps to determine what type of bond will be formed when two elements react, right? There's ionic, polar covalent, and non-polar covalent, which we'll talk about all of those. And they help to understand elemental properties like melting point, boiling point, and density. So here's a little diagram. You can pause the video and really check this out. But you'll see that we've got here atomic radius, electronegativity, and ionization energy. So those things that have very low or very high electronegativity and ionization energy tend to have low melting points. Whereas the things in the middle that have medium electronegativity, medium ionization energy, medium atomic radius, they have high melting points, right? This is because they're not pulling electrons very hard, they're not giving up electrons a lot, and so they're just stable on their own, they're doing their own thing, minding their own business. And like I said, they tend to be largely more unreactive. They tend to have high melting points. And so that tends to be all of the stuff in the D block, right? All that stuff tends to be more unreactive, higher melting point, but also lower electronegativity, medium ionization energy, right? They're just kind of there hanging out. Okay. Activity series. This is something that we will familiarize ourselves with. And this is when things are reacting, right? Like especially in solution, what is going to react preferentially with things over what else, right? So all the things on this side are positive ions, all the things here are the negative ions, and really it's just the halogens that we're looking at. And so on the positive side, right, we've got stuff that's really reactive like lithium, potassium, calcium, sodium, right? You probably know all of those. They're up in the upper left-hand corner, and they react pretty well. They are highly active, which means that given the choice between like sodium and say copper, in solution, a negative ion will preferentially react with sodium rather than copper. Oops. And so this, right, reactivity decreases, so we get less reactive until we're down at like platinum and gold that really hardly react with anything. So when we're looking at this, right, highly reactive, things are going to preferentially react with that, right? All the way down to gold, which really things just ignore for chemical reactions. All right, and it's the same over here on this side, fluorine being the most electronegative and extremely reactive is the most reactive, and then as you go down, right, iodine here, it will react with stuff, but if there's a positive ion, it will preferentially react with fluorine over any of the other halogens. All right, so basically this is telling you preferentially in a chemical reaction or in a solution, right? You've got a bunch of chemicals dissolved. The things up at the top are what chemicals or other atoms will preferentially react with. They are more active or reactive than the stuff down at the bottom. Okay, so to wrap this up, things to remember: effective nuclear charge is central to why all the trends work the way they do, right? How strongly the nucleus is pulling on those valence electrons and how much shielding there is. Electronegativity is going to be important to remember. We'll come back to it throughout the year. The trends help us understand and predict elemental properties, and the trends are directly a result of the electron configuration in atoms that we have been talking about recently. All right, thank you, and I will see you in class.